Okay, so hello and welcome back. So in this video what I want to show you is how you can basically do a couple of calculations to turn a transistor on. And what I mean by that is basically they call this to turn a transistor on, or basically they call it saturation. So you can use any of these terms and they mean the same thing. And basically I'm specifically talking about bipolar junction transistors. Bipolar junction transistors. And these are also called BJTs, and there's two types of them. There is the NPN type and there is a PNP type. The NPN type, the PNP type is almost never, I mean it's used only very rarely, not that often, so we are not talking about that here. We are talking about the NPN transistor, right? So basically, and the reason why you do this is I mean there is many different types of reasons why you would want to do this, but the simplest thing that you could say is that, for example, you have a power supply here and you have a load over here. If you connect this load to, or suppose that this is a lamp, connect this power supply to this lamp starts glowing, right? And you can control this using a simple switch. You can put a switch over here and then you can turn this on and off, right? Now you can use one of these transistors so that it does the same thing for you, and of course then you don't have to basically then you don't really have to basically do this manually anymore, meaning that you can put this lamp in a circuit containing one of these transistors, and then basically the input of your transistor is not then manually controlled. It is controlled by some signal, for example, coming from some other circuit. For example, you are basically working on an Arduino or something like that, a microcontroller or something like that, and then basically the output of your microcontroller goes high, and then that voltage goes to the input of the transistor, or the base of the transistor. Essentially, the base of the transistor means that it's like turning the switch manually on, and then the transistor will turn the lamp on, turn the lamp on for you, basically. So that's basically how you do this. Now, in case you didn't understand my explanation, that's how it goes. So essentially you have this transistor over here. This is the base of your transistor, and this is the collector, this is the emitter of the transistor. So base, collector, and emitter. This is an NPN transistor, so you connect this emitter to the ground, which is your negative supply. The load over here is connected to your collector, and then this goes to the positive supply, right? Now this collector emitter junction is functioning like a mechanical switch over here. Whenever this switch is turned, is on, meaning that it is connected, then of course your lamp is and of course this can be any sort of load. Basically it can be anything, but essentially whenever this switch is closed, then basically you have the positive rail connected to the load, and the negative rail is connected through the switch to the load, and then the lamp starts glowing. And then this base of the transistor is you can give it some signal coming from, for example, as I mentioned, from some Arduino or some microcontroller or some other circuit. Basically you can have any sort of circuit over here that has some output. This output comes over here, and then basically the output of this circuit is essentially controlling your load over here, meaning that you can turn your load on and off. And then this mechanical switch becomes this collector emitter junction, right? So now you can of course do all kinds of things using this collector emitter junction, meaning that you can use it in an amplifier circuit. You can use it in a I don't know, oscillator. So you can do whatever you want to do with this, but in this case we want to use it only as a simple mechanical switch, right? So the way that you do that is that essentially, the exact same way. So you connect your transistor this way. There is usually a resistor over here which is called R of B, and let me draw this way. There is usually a resistor over here which we call R of B, for example, because this is the resistor connected to your base. This goes to the base of the transistor, and there is the collector and emitter of the transistor. The emitter goes to the ground, and then your base goes to your collector is connected to the load, and then the load is connected to the positive rail, and of course this base has to be connected to the positive rail as well. So this becomes V of S, for example, positive, and that's basically how you do this. Now what I'm going to do is that I'm going to substitute this load with a simple resistor. I'm going to draw a resistor over here, and I'm going to call it R of C, right? That means that basically whenever this actually does act as a closed mechanical switch, some current is going to be going through your resistor, and that's basically how this circuit works, right? Now one more thing that you need to pay attention to here is that if I call this V of C, meaning that the collector voltage, then basically if the whole supply voltage is dropped across this resistor over here, then this V of C is going to be equal to 0, because because you have the positive rail over here, the negative rail over here, and this resistor over here and the collector emitter junction of the transistor are basically connected in series. The way that this transistor works is that basically whatever the voltage drop across this resistor is going to happen based on Ohm's law, meaning that V is equal to IR is going to be working for you here. And if you basically have the sort of current over here through this resistor, depending on the value of your resistor, some voltage is going to be dropped across this resistor, right? That voltage can be controlled. The voltage dropped is a function of essentially the resistance of this resistor and the amount of current going through that resistor. That current can be controlled, right? It can be controlled using the current that goes through the base of your transistor, the ground. And basically this base current that goes to the ground is controlled by this resistor, because you have the V of S over here, and when you change the value of this resistance, the value of this resistor, essentially the current changes over here. It's just like a simple resistor connected to a power supply. Depending on how much resistance you have over there, the current changes, of course, right? So what I'm going to do is that, and there is a relationship between these two currents. The current going through this branch over here, which I call I of B, and the current going over here, which I call I of C. Now this I of C to I of B is called basically the beta of your transistor, or the gain factor of your transistor. So every transistor, and this gain factor is essentially set for every transistor part number that you might have. So for some transistors, the value of this beta is, for example, I don't know, 50. For some transistors, it's equal to 100. For some transistors, it's equal to 200, 300, and so on and so forth, right? So that means that if I know the value of my beta, and if I know the value of the base current, this base current, I can control it. There is no problem with that. I can change this resistor over here, the base current changes, and I can control this current through the base emitter junction. So I can control this, and I know the value of this. The value of beta I know based on the part number of the transistor, and then as a result I know how much current is going through the collector, and that's the whole story, right? So now let's do a concrete example here to see how we can actually turn this transistor on, and you will understand completely what I meant by all of this. Let's say that in the exact same circuit you have the value of this, and one of these basically is usually set. Usually R of C is set, for example, and then you, based on that, you have to change the R of B, or R of B is set, and then you have to change the R of C, or both of them, or basically neither of them is set. And neither of them is set, and you can make changes in order to get to different situations with this transistor. But in this particular case, let's say that your R of C is equal to, for example, 4.7 kilo. And let's say that the value of your beta is equal to, for example, 50, right? So if that is the case, then essentially I know how much current is supposed to go through this resistor, so that the voltage drop, and let's say that basically your V of S is equal to 10 volts, right? And one more thing that you need to note here is that there is, any NPN junction that you might have, for example, a simple diode, for example, you know that there is a voltage drop across any silicon diode, which is something about 0.7 volts, right? And a transistor is the same story, meaning that the same 0.7 volts is going to be dropped across the base emitter junction and across the collector emitter junction. But in case your power supply voltage is greater than or equal to 10 volts, for example, then you can ignore basically all of these voltage drops of 0.7 volts across all of these junctions, because then it's not going to be important, meaning that it's just not important, because all of these resistors and everything that you use over here, basically they have their own tolerance of 10%, 20%, 5%. So this 0.7 volt voltage drop over here is not going to be that important in calculation. But if your supply voltage is, for example, something like, for example, 5 volts, then basically you need to take these voltage drops into consideration, because this is like for example 1/5 of this voltage is like, for example, something like 1/5 of this voltage over here, and in such cases basically this is important. But in this case, where our supply voltage is 10 volts, you can ignore all of these voltage drops, and you can assume that there is no voltage drop across these PN junctions, right? Now what I'm going to do is that I'm going to create the kind of current in this branch, so that the whole supply voltage is dropped across this resistor. If that happens, then there is no voltage left to be dropped across this PN junction. And when that happens, basically we say that the transistor is saturated or turned on, meaning that there is no voltage drop across the collector emitter junction, meaning that it is functioning as like a closed mechanical switch. A closed mechanical switch, basically what happens in the case of a closed mechanical switch is that if I close the switch, the resistance across the terminals of the switch is essentially 0 ohm, and V is equal to IR tells us that if R is equal to 0, then V is going to be equal to 0. That means that the voltage drop across the switch is going to be 0 volts, right? If there is some resistance across these two terminals, of course there is going to be some voltage drop across the terminals. But since when you close the switch, the resistance is 0, the voltage drop is going to be 0. So I'm going to create the same situation over here, where meaning that I'm going to make some arrangements so that the voltage drop across this collector emitter junction is 0, so that this is acting exactly like a closed mechanical switch. So how do I do that? I need to basically make sure that the whole voltage, supply voltage, is dropped across this resistor over here, across R of C. And I can apply the Ohm's law to R of C, meaning that I can say that basically V is equal to IR, and I want the voltage to be 10 volts, the voltage drop to be 10 volts. So I write 10 volts over here, and we calculate the current for that, and the resistance over here is 4.7 kilo ohm. 4.7 kilo ohm. That means that the current is going to be 10 volts divided by 4.7 into 10 raised to the power 3 ohm, which is the same thing as basically 10 divided by 10. So you can simplify this and write this as 10 raised to the power 2, and 1 divided by 4.7 is the same thing as 0.21. I'm going to take two significant figures, not more than that. So that's 0.21 into 10 raised to the power negative 2. And the unit would be amps. So that's the same thing as essentially the same thing as 0.0021 amps which is the same thing as 2.1 milliamps, right? Which is the same thing as 2.1 milliamps. Is that correct? I'm not really sure. My mind is a little bit tired right now, so I don't want to do. So basically I can write this as 0.0021 into 10 raised to the power, so that's milli 10 raised to the power negative 3 and amps. And I'm going to write this as so 0.0021, I can write it as, essentially move this 3, basically 2.1 into 10 raised to the power negative 3, right? That's correct. So I can write this as 2.1 into 10 raised to the power negative 3 into milli over 10 raised to the power negative 3 amps, and these two will cancel out, so that's 2.1 milliamps. So that means that the current that I need over here, that means that the current that I need over here, the current that I need to go through this resistor over here, is supposed to be 2.1 milliamps, right? So that means that basically I of C, that means that I of C is supposed to be 2.1 milliamps, so that the whole voltage, the whole supply voltage is dropped across this resistor, and then there is no voltage drop across this PN junction, and then this becomes a switch, essentially, right? Now this is the current that I need to have over here, and in order to get the transistor to draw this kind of current from the supply volt, from the power supply, I need to play with this equation over here, meaning that we said that basically I of C to I of B is equal to beta. And the beta of your transistor is in this case 50. So I can write basically over here, I can write 50 is equal to I of C, which is 2.1 into 10 raised to the power negative 3 amp, and divide that by basically I of B, and that tells me what current has to be flowing into my base, so that this current is flowing into my collector, right? So then what this means is that then 50 times I of B is equal to 2.1 into 10 raised to the power negative 3 amps, and these are all in amps, so I will not write that. So I of B is equal to 2.1 into 10 raised to the power negative 3 divided by 50, right? So that means that whatever this current is that is supposed to be flowing through your collector, the base current is going to be 50 times smaller, right? So now what is 2.1 divided by 50? That's 0.042. That's 0.042 into 10 raised to the power negative 3 amps. So I of B is supposed to be this current over here. Now you can write this as now I'm not going to make conversions and things like that over here. It's unnecessary, really. So this current, I need to have this current flowing through my base, right? So then how do I do that? So there is a 10 volt supply on this resistor. So if I choose the resistor properly, the same current that I need over there will be flowing through the resistor, which means that I simply have to apply the Ohm's law to the resistor, to the R of B. So the voltage across this resistor is 10 volts. The current that is supposed to be flowing through that resistor is 0.042 into 10 raised to the power negative 3 amps times R, and this is the value of the resistor that I need for my base. So that means that R is going to be equal to 10 volts divided by 0.042 into 10 raised to the power negative 3 amps, and that is the same thing as essentially this goes to the numerator. This becomes essentially 10 raised to the power 3. So I can write this as times 10 raised to the power 3, and then these two together, that becomes 10 raised to the power 4, and then 1 divided by 0.042 is equal to 23.8. I'm going to write that as 24. So 1 divided by 0.042 is equal to 24, and this is 10 raised to the power 4, and then volt divided by amp is equal to ohm, right? So that means that R of B is supposed to be 24 into 10 raised to the power 4, which is 240 kilo ohm, right? So that is the resistor that you choose for your base. And let me see if my answer is correct. 240 kilo ohm, right? So I hope that you have understood this. If you haven't, there is no problem. I'm going to do another video essentially solving the same type of question. So I'll see you in the next video with the same type of question. Thank you.